All right, let's get started. So first of all, one announcement regarding lab number 4. Because we are still discussing MOSFETs and we haven't covered MOSFETs in a lot of detail yet in the class, what we are going to do is that again we are going to have lab 4 over 2 weeks. So even though in your canvas you'll see lab 4 is scheduled from October 9th to October 12th, we're going to have it from October 9th to October 19th. So that is next week. So again, depending on whether you want to do the lab this week or next week, you can choose any one of the 2 weeks to complete the lab. So if you are comfortable with doing the lab this week, please go ahead and do it. If you are not comfortable doing the lab this week, you can do it next week. Okay. And I'll inform the UPIs accordingly. Hopefully by next week we'll cover everything that is required for you to complete the labs. All right, any questions? If not, we had been discussing physics of MOSFETs in the previous few lectures, and what we did in the last lecture is that we tried to understand how the energy band diagrams should look like for, let's say, a p-n junction diagram. That if you have a semiconductor which is doped with p type, or if you have a semiconductor which is doped with n type, you can probably already draw how the energy band diagram would look like. Now, for p-n junction diode, it was easy. For MOSFET, it will be a little bit more complex. Why? Because again, MOSFET is a more complex structure. p-n junction diode was just a p-type semiconductor along with an n-type semiconductor. But for MOSFET, you basically have this. Let me draw it somewhere over here. So you basically have the gate. So let's call this region as the gate. You have a oxide region in between. So that's the oxide. Gate in most cases it will be a metal. So let's call it a M as well. And then you have an oxide, and then you have a semiconductor. So that's your MOS structure: metal, oxide, and semiconductor. And as some of you have already pointed out, that this metal oxide semiconductor structure gives you a capacitance. So if you follow your device physics classes, you'll know that there is something called MOS cap, and that's exactly this capacitance which is formed using the metal and the semiconductor while the oxide is sandwiched in between. So that gives you the MOS structure. But along with the MOS cap structure, you also have the source and drain region. So let's say you have a source and you have a drain. And if it is a n-type or n-channel MOSFET, then the source and drain regions will be n-type, whereas the bulk will be p-type semiconductor. So your bulk or the body region will be the p-type semiconductor, whereas your source and drain will be n-type. Now imagine that you're cutting this MOSFET across this line. So I'm drawing maybe let me draw it with a new color. So let's say you are cutting the MOSFET across this line. So you basically have an n-type region on the left, you have a p-type region in the middle, and again an n-type region on the right-hand side. Okay. So if you take a line and cut the MOSFET across that line, this is how it will look like. Now the energy band across that line will look something like this, which is shown in this particular slide. Why is that? Because on the left-hand side you have an n-type semiconductor, in the middle you have p, and again on the right-hand side you have n. So just by cutting the MOSFET across this line that I have shown here, you will have an n, then a p, and then again an n region. Now you already know from the previous class is that if you have an n-type semiconductor, you have an excess of electrons. If there are more number of electrons, the average energy will be lower. Again, why is that? Because the energy of one electron is minus q times v. If you have more and more electrons, the average energy in that entire region will be minus, let's say, n times q times v. And so it will be more negative if you have more number of electrons. So wherever you have an n region, the energy will be lower in the band diagram. If you have a p region, the energy will be higher. And again, you have an n region, so the energy will be lower. So that's why you have this kind of a band diagram where on the N side, on the left-hand side, you have lower energies. In the middle, you have higher energies. And on the right-hand side, you again have lower energies. Now, what you're trying to do here is that you're trying to, so this is your source, right? In the left-hand side, you have the source. In the right-hand side, you have the drain. You'll eventually try to send some of the electrons from the source side to the drain side, right? Now, as the electron is traveling from the left side to the right-hand side, it encounters this barrier. So this is like a mountain, this is like a hill, and let's say you're trying to just roll a ball across the ground so that you can reach the other side. So just think about it in this way, that analogy, that you're trying to roll a ball from the left-hand side to the right-hand side. So you push it with some amount of energy, but there is a mountain in between, there is a hill in between. So the ball can only roll through to the right-hand side if it has enough amount of energy, right? Or it can easily roll to the right-hand side if you lower the height of the hill. That's also a possibility, that in some way, if you can lower the height of the hill, if the height is reduced, then the ball can easily roll from the left-hand side to the right-hand side. And that's what we'll study next, which is called the threshold voltage of the MOSFET. So this is something that you have learned in the previous lecture, that if you apply a positive voltage, the energy comes down for the electron. Because again, the energy of the electron is minus Q times V. So if you are applying a positive voltage, minus Q times V will be more and more negative. So it will come down. Okay? So just like having more number of electrons reduces the energy, also applying a positive voltage reduces the energy. So as you apply a threshold voltage across this hill, the height of the hill will be lowered. So you'll have something that will probably look like this as you apply the positive voltage at the gate. And then it will be easier for the ball to roll through from the left side to the right-hand side. So that is basically your concept of the threshold voltage. And as I said, that it's easier to understand the concept of the threshold voltage from the energy band diagram, because now you can easily visualize this, that you are trying to roll this ball from left to right. And as you reduce the height of the hill, you can easily get the ball through from the left to the right. All right. So this is what we'll be explaining in the next few slides, but I have already told you what we are going to discuss next. So again, E equal to minus Q times V, that's the energy of the electron. And at the source side, you have lower energy. In the channel, you have more energy. And at the drain side, you have, again, less amount of energy. As you are trying to put this electron or the ball from the left side to the right-hand side, you see this energy barrier. And to cross this energy barrier, it either needs to have a lot of energy. Sometimes you may have heard about something called a tunnel diode. So a tunnel diode is something where this channel region is, let's say this energy barrier is very thin. So instead of having such a thick energy barrier, let's say you had something like this. Then if this electron has enough energy, it can just tunnel through from the left side to the right-hand side, and that's the concept of a tunnel diode. We're not going to discuss tunnel diode here in this class, but this is related in this way, right? So again, if you try to understand everything from basic physics, you'll see everything is connected. So for the MOSFET, you generally cannot have a very high amount of energy for the electron so that it can tunnel through this energy barrier. So what you'll need to do, you need to reduce this energy barrier. You need to reduce the height of this hill so that the ball can roll through from the left side to the right-hand side. And that's something you'll do by applying a positive gate voltage VG at the gate. So as you apply the positive gate voltage, the energy of the gate or energy of the P-type semiconductor in the channel region, that will come down. Okay. And now you can transfer some electrons from the left side to the right side. You can also transfer, depending on how you apply the polarity or the voltages, you can transfer the electrons from the left side to right side or right side to left side. Okay. All right. Now this is all at a drain to source voltage of 0. So this is your source, this is your drain, and in between you have your gate. So you are applying a positive gate voltage, or you are applying a positive gate to source voltage, because source is usually grounded for the MOSFETs, for the N-channel MOSFET, and we'll discuss why the source is grounded. So if you think about the MOSFET structure, you have again gate, oxide, and semiconductor. And also you have this N-channel source and N-channel drain, or N-type source and N-type drain. The body is P-type. Now what we are saying is that we'll ground this source. So let's say the source region is grounded. The gate region is where you'll apply the VG voltage. So you'll have a positive VGS. At the drain, you can also apply a voltage which we haven't discussed yet, but we'll discuss in the next few slides. As you are connecting the source to the ground, you also need to ground this bulk or the body region of the MOSFET. Why is that? Because this is P-type semiconductor and this is N-type semiconductor. As you are applying a ground to the N-type semiconductor, if the P-type semiconductor has any kind of positive voltage, you'll see a forward bias PN junction diode. So this P-type will be connected to positive and the N-type will be connected to ground. So there will be a forward bias current flow from the P-type to the N-type. And that is something you don't want because you don't get any advantage out of that current. You just consume more amount of power, but you don't get any advantage. So that's why you'll generally want to reverse bias the PN junction diode between the body and the source. That's the reason why for an N-channel MOSFET, you'll connect the body to a ground. Instead of connecting it to any voltage, you'll connect the body to ground for an N-channel MOSFET. Similarly, for a P-channel MOSFET, you'll connect the body to the highest voltage in the circuit, which will be your VDD. So for a P-channel MOSFET, you'll always connect the body to VDD. For an N-channel MOSFET, you'll always connect the body to the ground. That's a very important thing to remember, because without that, none of your circuits during your labs or in your simulations will not work. Okay. So this is without applying any kind of gain to source voltage. As you're applying a gate to source voltage, the height of the hill comes down. That's the only thing that we have discussed till now. But VDS, or the drain to source voltage, is still 0. And if the drain to source voltage is 0, you'll not have any kind of current flow. Because again, the current flows from the drain to the source region for the N-type MOSFET, or the electrons flow from source to drain, so the current will flow in the opposite direction. So that will be the drain to source. But if you don't apply a voltage between drain and source, there will be no current between drain and source. Right? That's just your KCL and KVL. That okay, you have an element. If you don't apply any voltage across it, there will be no current through it. So as your VDS is 0, the current through the MOSFET is equal to 0. And you can also understand it from this perspective, that okay, you have reduced the height of the hill, but you are not rolling the ball. The ball is stationary in the source region, for example. So it cannot, even if the height of the hill is reduced, even though height of the energy barrier is reduced, the ball cannot roll through to the right hand side because you're not rolling it, you are not providing it any kind of energy. Okay. So that's what will happen when your VDS is equal to 0. What will happen if you apply a small drain voltage? As you are applying a small drain voltage, your VDS becomes more than 0. So the energy on the right hand side will come down even further. So you had already reduced the energy below the gate by applying a positive gate voltage. By applying a positive drain voltage, so let's say you apply a positive drain voltage here and assume that the source is always grounded. So you are applying a positive VGS, you are also applying a positive VDS. So VGS is more than the threshold voltage and VDS is more than 0. In that case, the energy on the right hand side, the energy below the drain or energy at the drain region will be even lower. So in this case, what will happen is that as you are applying more and more drain voltage, the slope of this energy curve that will change. Let's say you apply a very small amount of drain voltage and the curve looks like this. You apply more amount of drain voltage, the curve will start looking like that, right? So the slope will increase as you apply more and more drain voltage, because on the drain side you'll have more and more reduction in the energy. If the energy is reduced on the drain side by more and more amount, the slope will increase by more and more. which means that if you start rolling a ball from the left hand side, it will be easier for the ball to roll over to the right hand side as you are applying more and more drain voltage. So the current, the rate at which the balls are rolling, the rate at which the electrons are going from left to right, that is basically your current. So the current will increase linearly as you are increasing the VDS. As you increase VDS, your drain to source voltage, the slope of this energy barrier will be more and more. So the current through the device will be more and more. And now you go back to your ID versus VDS characteristics. I'll draw it here. So if your VDS is on the x-axis and your ID, that is the current through the device, is on the y-axis, you saw that this profile looks something like that. That at small VDS, as you are increasing the VDS, the current through the device keeps on increasing. That explains this region. That okay, as you are increasing the drain voltage, the energy on the right hand side goes down, and the slope keeps on increasing, so you get more and more current. So that explains this linear region of the ID versus VDS characteristic. Next, we'll discuss why you have a saturated ID as you are having more and more drain voltages. As you have a higher amount of VDS, your current kind of saturates. And why is that? Okay. But before that, I think there are a few more slides over here. So as you are increasing the drain voltage, what I explained in the previous slide, as you are increasing the drain voltage with a high amount of gate voltage, your slope keeps on increasing. So for example, initially the slope was something like that. Now you have increased the drain voltage much more. So you see something like this in the energy diagram. So it's very easy for the ball to roll through to the right hand side as it crosses only this much energy barrier. So it does not need to go through this path, but instead, as you have a higher amount of VDS, the ball can easily roll through this. Now, if you remove the gate voltage, what will happen? If you remove the gate voltage, the threshold voltage, the amount of, again, what is the definition of the threshold voltage in this context is that the amount of voltage that you need to apply to the gate so that this barrier is reduced by a large amount. We'll discuss by how much amount it is, so that it becomes easier for the electron to pass from the left side to the right hand side. So that's your threshold voltage, that you are applying a gate voltage, a positive gate voltage for the n-channel MOSFET, so that the electron can pass through from the left side to the right hand side. But if you remove the gate voltage now, the energy barrier will come back to its original position. So for low gate voltages, you'll again get something like this. But at so low drain voltages, you'll get something like this, and high drain voltages, you'll get something like that. So again, it is hard for the electron to pass through this energy barrier as your gate voltage is 0 in this case. So even if you are applying a high amount of drain voltage, the electron will not pass through from the left to the right. So this is just some figures or empirical figures from experiments for different kind of MOSFETs. As you are applying, for example, higher and higher VDS, the reduction of the energy band is shown here. So this is from real devices. So you can see that really, as you're increasing the VGS, the energy barrier goes lower and lower. As you are applying a drain to source voltage, the energy on the right hand side goes lower. And this is the ID versus VDS characteristic for different VGS. That's what you see in the middle. And that's something we had discussed in the previous few slides. Now, except for one thing that we have not discussed, that why the current will saturate at very high VDS. Now, at very high VDS, what you can assume that as you're applying higher and higher VDS, at some point, your energy band diagram would start looking like this. That you'll have your source region, your channel would be at the same energy as your source region, but the drain will be at a much lower energy. Now, in this case, even if you're applying higher and higher VDS, let's say you have applied a VDS for which the energy band diagram looks like this, versus you are applying more VDS for which the energy band diagram looks like that. In both cases, it will be saturated by the number of electrons that you have in the source region. If you do not have, as you have a number of electrons in the source, all the electrons can, or all the balls can roll through this slope and be delivered at the right hand side. As you have applied a large amount of VDS, you will see at some point you will be limited by the number of electrons that are present on the source side. And in that case, your current will be limited. That's what you are seeing over here, that even though you are increasing your VDS more and more, your current will be saturated because it will be limited by the number of electrons that are present on the left-hand side at some point. That's again an intuitive explanation. We'll look at the equation-based explanation in the next few slides. Okay. So, if you try to do a mathematical treatment of the MOSFET, again, let's say you have applied a ground or a zero voltage to the source, you are applying a VDS to the drain, and you are applying a VGS to the gate. In the channel, you will have a certain amount of charge, Q, and that certain amount of charge can be represented using the equation Q equal to CV, so capacitance times voltage. Now, what is the capacitance in the channel? You know from the formula of capacitance, it's epsilon A over D, where epsilon is the permittivity of the material, A is the area of the capacitance, and D is the distance between the two plates. Now, of course, in this case, where is the capacitance? The capacitance is in between the metal gate and the semiconductor material, where the insulator is the oxide layer. So the thickness or the distance between the two plates will be exactly equal to the thickness of the oxide layer. So that's why you have TOX, which is the thickness of the oxide layer, that determines the distance of the two plates in the capacitance. Epsilon is, of course, the permittivity of the oxide layer, and A is the area of the gate, or area of the capacitance. Now, area of the capacitance will be equal to the area of the gate. Let's say the gate has a length of L, and it has a width of W, which I had explained in a previous lecture, that is in the third dimension. So this is a two-dimensional picture of a 3D structure, right? So this is across a cross-section of the MOSFET, but the MOSFET is actually three-dimensional. So in the other direction, so if you draw a 3D figure of the same thing, so in the other direction, the width will be this much. The width of the structure will be the dimension which goes inside the slide or which goes inside the page. So your A will be L times W. That would be your area of the capacitance. You can, in case of mathematical treatment of a MOSFET, there is a term called COX, so capacitance of the oxide, and that is usually defined as the unit capacitance or the capacitance per unit area for the oxide layer. So C divided by A, or epsilon OX divided by TOX, that is defined as your COX. So the unit for COX or oxide capacitance is farad per centimeter squared, because you're taking the capacitance per unit area. So that's a very important terminology in case of MOSFET equations, that whenever you talk about COX or the oxide capacitance, it is per unit area. Okay, because if you have a larger MOSFET, the capacitance could be larger. If you have a smaller MOSFET, the capacitance could be smaller. But the capacitance per unit area will always be the same. Okay, now that's the definition of your C. What is V? What is the voltage in this context? The voltage in this context is defined basically your VGS or gate to source voltage minus the threshold voltage. And again, why is that? That's the voltage that is available across the channel. So you are applying a VGS at the gate, but if your VGS is not more than the threshold voltage, you will not have any kind of current flow through the device. Again, similar to the concept of threshold voltage in the diodes, you have to apply a certain amount of positive voltage, which is more than the threshold for the MOSFET, for it to carry current. So that is something you can sort of visualize as the voltage drop across the gate and the oxide. So if you have a threshold voltage of VTN, which says that it is an N-channel MOSFET, at the channel, the voltage that is available is VGS minus VT. Right? Gate to source voltage is something that you are applying here at the gate. But if the gate to source voltage is not more than the threshold voltage, you don't see anything at all. So the effective voltage that you are interested in the channel is by how much your VGS is larger than your threshold voltage. So VGS minus VT is called an overdrive voltage. So by how much you are overdriving the channel as compared to the threshold voltage that was required, and that's the definition of V overdrive. So your C is equal to, let's say the oxide capacitance is epsilon OX over TOX, and your V overdrive is VGS minus VT. So the charge per unit area in the channel is minus COX times VGS minus VT Farad per centimeter square. So this should be Farad. Or sorry, this is Coulomb. That is fine. So because we are talking about charge now. So this is Coulomb per centimeter square. That's the charge that is present per unit area in the channel. And again, you are applying this simple formula Q equal to CV. You are just writing down what is your C and what is your V. Now, if that is the channel charge, that is the charge that is present in the channel, you can find out what is the current that is present in the channel. And for that, what you usually do is that you know about the amount of charge that is present. That's per unit area. Now, if you let's just assume that you have a bar of semiconductor. So maybe let me go it in here. So let's just assume that you have a semiconductor bar. So it's just a rectangle that I'm trying to draw here, or basically a parallel pipe. That's what I'm trying to draw here. Now, if you take a cross section of this, so let's say you just assume that this is the cross section. The charge, total amount of charge divided by the cross-sectional area, that gives you the charge per unit area, right? But when you talk about current, you talk about the total amount of charge that is moving through this structure, this parallel pipe, and the total amount of charge that is moving through this parallel pipe will be proportional to the width of it, right? So if this is the width, if this is the width of the structure, the total amount of charge that is moving through it will be proportional to the width. Correct? Because if there is an electron over here, there is an electron over here, there is an electron over here, and all of those electrons are moving. So the total amount of charge will always be proportional to the width of a structure. This is something similar to when you studied the equation of a resistance, that resistance is rho L over E. Why is that? That when current flows, the current is proportional to the width. So if you have the current proportional to the width of the structure, you're taking the amount of charge that is present in that particular width of the MOSFET. And then what you have over here is this this term, the Vx, that is mu times the epsilon. So this is called the velocity of the electron. So basically you have a certain number of electrons. So you're taking the concentration of those electrons per unit area, multiplying it with the width, and multiplying with the velocity of those electrons. So again, go back here, that you have certain amount of electrons in this unit area, or let's say this particular cross section, you have a certain number of electrons. These electrons are moving from left to right with a certain velocity. Right? So let's say the source region is on the left side, the drain region is on the right side. So the electrons will be moving from the source to drain with a certain amount of velocity. The current will be proportional to that velocity. The current will also be proportional to the width of the bar. If the width is more, the current will be more. If the velocity is more, the current will be more. So your total amount of current will be the channel charge multiplied with the width multiplied with the velocity of the electron. you already know what would be the total amount of charge, and you will know what would be the velocity of the electrons. Again, this comes from a theory in your device physics classes, that the mobility of the electrons multiplied with the electric field where you are subjecting the electrons to, it basically gives you the velocity of the electrons. So mu times E gives you the velocity of the electrons. And also you know that the electric field is minus dV dx. So basically if we have a length of L, the voltage across drain to source divided by the distance between drain to source, that will give you the electric field between drain to source. So you can put all these values, that what is your Ex, what is your electric field, what is your velocity of the electrons, what is your charge per unit area in the electron, and eventually you'll come up with this equation, that the current will be equal to W over L times mu n Cox times Vds minus Vt times Vds. So that basically says that the current in the MOSFET device is proportional to the W over L ratio. So the width over length ratio, which is called an aspect ratio of the MOSFET. So the aspect ratio is something that is very important when you will be solving any problems related to the MOSFET. So this is called the aspect ratio. So when you are asked that design a MOSFET based circuit, what you are basically asked is that find out this aspect ratio, find out this W over L ratio, and that is what is called designing a MOSFET based circuit. So we'll be designing amplifiers and filters and so on, and whenever we are talking about designing, it's basically finding out what would be the correct W over L ratio for your MOSFET. And that is also called the aspect ratio. That multiplied with mu n times Cox. I'm not doing the entire derivation, it's just that you basically put these values over here, and then you can, so this is your ID current equation. You put all these values which are written below this equation to come up with the equation on the right hand side. Okay, so mu n times Cox. So the mobility times the oxide capacitance per unit area. That is a property of the process, property of the, let's say you are fabricating this MOSFET, or you are creating this MOSFET in the foundry of TSMC, versus you are creating the same MOSFET in Intel's foundry or global foundries. So these are different manufacturers or vendors of MOSFETs, and if you are creating this MOSFET in different foundries or using different vendors, the mu n times Cox could be different, because the mobility of the electrons could be different for different foundries. The capacitance per unit area can also be different as they are creating these MOSFETs. So it's called a process transconductance parameter. So why is it called a transconductance? Because again, you have a voltage term, which is the gate to source voltage minus the threshold voltage, that's the V over time, times VDS. So you have a voltage term to be a transconductance, right? Current equal to transconductance times voltage, or voltage equal to resistance times current. So everything except for voltages on the right hand side is a transconductance. Mu n Cox is called a process transconductance. That it's a function of the process. And what is meant by process in silicon design industry is that who is creating this MOSFET, who is building these MOSFETs? Is it TSMC? Is it UMC? Is it Global Foundries? Is it Intel? So everyone will have a different value of this mu n Cox, even though they are trying to design the same MOSFET. And that's why you'll see that if your laptop has an Intel processor versus an AMD processor, even though the speed of the processor is same or all the specifications are same, the performance will not exactly be the same. That is because the process is a little different. And by process, what is meant in semiconductor fabrication industry is that how you are designing this MOSFET, or how you are actually creating the MOSFET, even though the design is same. So mu n Cox is called the process transconductance. Mu n Cox times W over L. So your process transconductance times aspect ratio is called the device transconductance. So why is it called a device transconductance? Because W over L is a property of the device, of the particular device. So as you are designing multiple devices in the same process, your mu n and Cox will probably not change much, but your W over Ls can be very different. Some MOSFETs can have a W over L of 100, some of them can have W over L of 10, some of them can have W over L of 1000, for example. So W over L is a property of the device. So W over L times mu n COX is called the device transconductance. Mu n COX is called the process transconductance. So MOSFET overall this transconductance parameter, which is basically the device transconductance, this is in most books you'll see it is represented as K times K subscript N, or you may also see it is represented as beta. So we know that beta was something that we discussed in our previous classes, and we called beta as a feedback factor. Yeah, in some books you'll see that the MOSFET transconductance parameter is also called beta. So those two betas are different. So this is not the feedback factor. This is just the transconductance parameter for the MOSFET. But so that we do not have any confusion, I am representing this transconductance parameter as K subscript N. But in some books, you'll see that it is represented with beta, and beta in that case will not be the feedback factor, it will be the transconductance parameter. The process transconductance is mu times COX, that is sometimes represented as K subscript N prime. So your Kn is actually your aspect ratio multiplied with Kn prime. And you can represent your ID, the final current, as W over L times Kn dash or Kn prime times VGS minus VT times VDS. Now, of course, this is again an equation that is proportional to VDS. So this actually represents the characteristic of the device in this region. But as you are applying a VDS on the x-axis, your current keeps on increasing. So as you are applying VDS, your current keeps on increasing, and that's what you have in this region of the MOSFET. But eventually, you'll see that the currents will saturate because of the factor that we had discussed earlier. That okay, after a certain point of time, you'll have your energy barrier will be decreased by so much amount that you'll be limited by the number of electrons that are present in the source region to determine the amount of current that flows from drain to source. Okay, again, aspect ratio is something that you'll be asked to find out whenever you are asked to design a MOSFET. So what we are being asked is to find out what is the W over L ratio. So W is the width of the MOSFET, L is the length of the MOSFET or the length of the gate. So that's the length below the channel, that's L. And W is the other dimension, the third dimension, which you see in this top view, that is your width of the MOSFET. Okay. Now, from the mathematical treatment, what is happening at large VDSs? So when you have, this is something we are trying to explain the saturation of the MOSFET. So for large VDS, when you have a large drain to source voltage, what is happening is that this is N, right? This is N-channel, N-type semiconductor. This is P-type semiconductor. As you are applying a positive VDS, you are reverse biasing this PN junction diode. You have a P region here, you have an N-type region here. As you are applying a larger and larger VDS, and remember that this is grounded, the source is grounded, the bulk is also grounded. As you are applying large and bulk is grounded because you do not want a forward bias current to flow from the bulk to the source. So this is something that you don't want, and that's why you're grounding the bulk, which means that as you're applying a positive VDS, your PN junction on the drain side that becomes reverse biased. So what happens in a reverse bias PN junction is that as you apply more and more reverse bias voltage, the depletion region keeps on increasing. So initially, let's say the depletion region had this much width. After some time, as you apply more and more drain voltage, the depletion region will be larger. The depletion region will keep on increasing as you apply more and more drain voltage. Now, what happens to the channel is that in the channel, what you try to do is that you try to pull in, you try to attract electrons from the bulk region or from the source region just below the gate, right? You are applying a positive gate voltage, which means you are trying to attract electrons just below the gate. But you know from your definition of depletion region is that there cannot be any major T carriers in the depletion region. As you are trying to attract the electrons from the bulk region to the region which is below the gate, but at the same time, if you apply a positive VDS, that will increase the depletion region over here, which means there will be no electrons near this drain region. So eventually what will happen is that instead of the source, drain, regions, and then a constant channel in between, your channel will start looking like something like this, a triangular channel. That near the drain, because you have a depletion region, the number of electrons that will be present near the drain will be reduced. So this is called pinch off or pinching off the channel. That as you are applying more and more drain voltage, your VDS is more. You can think about it in another way, that initially, let's say you did not apply any VDS and you had created a channel between the source and the drain region by applying a gate voltage. So as you apply a gate voltage, let's say your VGS is greater than 0, and by applying a positive VGS, you created a channel. So let's say this is your channel, what I'm drawing in red. Now as you are applying a positive VDS as well, what you are doing is that you are attracting some of those electrons from the channel to the drain side already. You were trying to create a channel by having more number of electrons below the gate. But some of those electrons you are pulling away, some of those electrons you are pulling into the drain region by applying a positive drain voltage. As you apply a positive voltage, the electrons will start moving into the drain, and then of course the concentration of electrons in the channel specifically near to the drain will reduce. Correct? So this is another way of understanding the pinch off. And the other way is that from the idea of depletion regions, the depletion region will not have the majority carriers, which means that it will be depleted of the electrons that you are trying to create under the channel or under the gate. So what is happening in this case is that when does the pinch off happen? First of all, the pinch off happens when the voltage at your drain side, so this corner, this junction of your channel and the drain, when the voltage at that point is equal to VGS minus VT. Okay, so you had applied VGS minus VT at this point. Again, let me draw this channel, and maybe the source region on the left and the drain region on the right. Source, drain, oxide, and gate. So you had applied a positive VGS at the gate, and the voltage that was available below the gate was VGS minus VT, because there is a threshold voltage drop. Because if you do not have if your threshold voltage is a positive quantity, you at least needed to apply that much positive voltage at your gate so that you start creating a channel, right? So the effective voltage available in the channel is VGS minus VT. If you apply, and because of the application of that VGS minus VT, you created some concentration of electrons below the gate. Now, if you apply the same voltage at the drain, so let's call it that you have applied a V overdrive voltage at the gate. If you apply the same overdrive voltage, V overdrive voltage at the drain, what will happen? That at this corner, whatever electrons were created because of the application of the voltage at the gate, all those electrons will be sucked in at the drain region, because the drain region also has the same voltage of V overdrive. So you are creating electrons in the channel region because of the V overdrive, but because the drain also has the same V overdrive, the electrons will be sucked into the drain, and you will have no electrons present in the channel near this corner. So the channel, instead of looking like this rectangle, eventually will look like this triangle, where the width of the channel or the thickness of the channel near the drain will be 0. So this is called the pinch off voltage, that if your drain voltage is equal to VGS minus VT, at that point your channel is pinched off. So the channel thickness becomes almost equal to 0. So in that case, what would be your channel charge? Your channel charge is not a constant quantity anymore. So in the previous derivation, we assumed that the channel charge is a constant quantity, which is equal to capacitance times voltage. And why it was a constant quantity? Because channel oxide capacitance was constant, channel voltage was also constant. So your channel looked like a rectangle in this case. when you apply a drain to source voltage, your channel looks like a triangle. It does not remain a rectangle anymore because of the pinch-off effect. So when you have a pinch-off, or basically when you do not even have a pinch-off, the channel charge will be a function of the voltage across different regions of the channel. You already had VGS minus VT, that is the voltage seen at the source side, but the voltage seen at the drain side will be very different, because you have a VGS applied at the gate and you have a VDS applied at the drain. So the voltage profile will also be something like this. That's the channel profile that you see. So the amount of charge in the channel will still be capacitance times voltage, but the voltage will not be a constant voltage. It will be a function of the distance. So if this direction is the x direction, the voltage in the x direction is something that you'll have to subtract from the VGS minus VT, which is the voltage at x equal to 0. And using this, if we again do the same calculations for the pinch-off region, if we again do the same calculations, you'll eventually come up with this equation. So I'm not going over the derivation. Please go over the derivation in this case, and you'll see that here, when you are considering pinch-off, as your drain to source voltage, will be equal to VGS minus VT at pinch-off, you do not have the VDS term anymore. Instead of VDS, you'll have another VGS minus VT. And that's what you'll see if you go over this derivation. And you'll see that the current will be half of W over L times V1 COX times VGS minus VT whole squared, which means that in this region, the current becomes a constant. And this can be also explained from the energy band diagram, that when the channel is pinched off, after that point, you'll always be rolling this ball from the left-hand side to the right-hand side, and you'll be limited by how many balls are present on the left-hand side. You'll not be limited by the slope of the energy barrier, or you'll not be limited by the voltages that you're applying at the gate or drain. You'll be limited by how many balls or how many electrons are present on the source side. Okay, so this is the most interesting property of a MOSFET, that in the saturation region, the current is not a function of the drain to source voltage. So this is something we did not see in any other device, that you apply a certain amount of voltage and you keep on increasing that voltage across the MOSFET. The current across the device remains constant. So which means it works as a constant current source, which is a very important property of a MOSFET as a device. So this works as a constant current source. And if you look into the equation, the ID is a function of the overdrive voltage squared. So by how much extra voltage you are applying at the gate as compared to the threshold voltage, the square of that will be proportional to the ID. So that's why MOSFET is called a square law device. Now again, there were many simplifications that we had used in when we derived this particular equation, and we'll see some of those simplifications that we had done in this particular derivation, and that's something we'll be discussing in the later classes. But for now, it will be enough to sort of say that the MOSFET is a square law device, that the current through the MOSFET is proportional to the VGS minus VT whole square, and that's why it's called a square law device. If you are applying a small overdrive, your current is small. You apply a overdrive which is 2 times higher, your current will be 4 times higher. Then you apply a overdrive which is 10 times higher, your current will be 100 times higher, and so on. You can also find out what is the output resistance of the MOSFET, and what is the resistance. Resistance is the ratio of voltage to current, right? So if you are increasing the voltage by some amount, if your current increases by, let's say you're increasing the voltage by X amount, if your current increases by Y amount, the ratio of X over Y gives you the resistance, right? So in the saturation region, in the ideal condition, since the current is a constant, the output resistance is infinity. So as you increase the voltage, your current does not increase, which means that the resistance is infinity. The voltage over current or the change in voltage divided by the change in current is an infinite quantity. So your output resistance in saturation in the ideal scenario is infinite. But you'll see that there is a non-ideal scenario as well when the MOSFET equation, instead of just this square law which we had studied earlier, instead of that it also has this 1 plus lambda VDS term. And this lambda VDS term, where lambda is called the channel length modulation parameter and VDS is the drain to source voltage. So there is a small dependence of ID over VDS, and that comes in because the channel length, the W over L that we are presenting over here, the channel length is actually a function of the drain to source voltage as well. Because as you are applying the drain to source voltage more and more, your depletion region widens. As your depletion region, the width of the depletion region changes, the effective channel length also changes. And that's why you'll see that there is a small dependence on VDS as well. And that's why for the MOSFET, the output resistance, instead of being infinite, it will be a large quantity. So the output resistance of a MOSFET is ideally infinite, and in the practical case, it's a large quantity. So we'll stop here, and in the next lecture, we'll be discussing some more details about the MOSFETs and how we can use this device in a circuit.